Hey, good afternoon. Let's quickly go over the solutions to the quiz that you just underwent. Okay, so this is a PN, this entire quiz is about a PN junction diode. I hope you realize that. Okay, so electric field distribution is given here. And basically, you should know that most of the depletion region exists on the lightly doped side. So the more heavily doped side would be the side where very little of the depletion region or very little electric field is dropped or voltage is dropped. So that would be the right side, which is the N side. Okay. So then from this slope, you know that slope is given by Poisson's equation to be proportional to the dopant concentration or the dopant density. And so just Poisson's equation here, hopefully it's relatively simple arithmetic and numbers usually come out very evenly in my quizzes. So there's just a matter of calculating the slope properly and setting that equal to minus q times Na over epsilon. And epsilon for silicon is just 10 to the minus 12 farad per centimeter. And then the built-in, the total voltage dropped across the depletion region is just the area underneath this triangle, or the magnitude is equal to the area under the triangle. So again, it's just 1/2 times minus 8 times 10 to the 4 times half a micron. So you just have to keep track of the units, make sure that half a micron is 5 times 10 to the minus 5 centimeters. Oh, 2 electron volts, okay. Yes. So it should be, yeah, VBI minus, all right. Yeah. You're right. So this is, I should get rid of the Q. Right. Okay. And this is, okay, so 2 volts dropped across a junction that's greater than the built-in potential. I mean, and the built-in potential is always less than the band gap energy. So, bless you. So basically, you should know it's reverse biased. And then finally, to just complete the energy band diagram, what I was looking for is that you knew that the energy bands are, EC and EV are higher on the P side, so that's like 1 point, and that the curvature is like bending downwards like this, not concave the other way, and that you sort of draw a uniform band gap. So those are 3 aspects we look for on that band diagram.
They're curving
right.
Because of?
Okay, so yeah, so so it's curving this way. Okay, so the curvature here, so remember the band edge, so E sub C or E sub V, is going to be directly reflecting the electric potential profile, except you just flip it. It's just opposite sign. Okay, so basically the gradient of the energy band edge is equal to the opposite of the gradient of the electric potential. In any case, okay, so the gradient is more shallow here. I mean, it's less steep here than it is here. And that's because the value of electric field is smaller here than it is here. Right, so that's why it should be concave this way. If you drew it the other way, like coming down faster and then gradually merging into EC or EV, then that would be kind of the wrong shape for the electric field.
Just a note on the quiz. My eyes.
What? Okay, wait. So, wait. So on part A?
Yeah, I thought you were asking for the more likely doped side, so I circled the other one.
How can I tell if you thought that? Okay. Okay.
Next time you could ask for the more lightly doped.
Okay, so next time I should ask which side is more lightly doped.
I read it both times as lightly doped, so I just feel really dumb about it now.
Okay. Okay, I'll. You just, oh my goodness. Okay. Okay, so does anybody have any questions about like whichever side? Is it? Do you all know that the lightly doped side is the side? Okay, all right. So maybe I'll just take off half a point because you guys really know it, right? Okay. I see. Okay. All right. So this is a new type of question, but basically to cover just current, to make sure you understand how current flows and how displacement current flows in a PN junction. Okay, so forward bias, if you decrease the doping on the lightly doped side, then the key is to know that the built-in potential is less, because if you have less heavily doped regions, then there's less of a dopant gradient, a concentration gradient of carriers. So you don't have to have as large of a built-in potential to counteract diffusion. And so when you apply a forward bias to allow extra carriers to go over the barrier, you actually get many more carriers if you have a lower barrier. So basically, bottom line is qualitatively, the forward bias current will increase if you have a lower built-in potential. Yes? So you use an equation to explain. That's fine. But yeah, that's basically what I'm looking for. It's just you have a lower, okay, there's two parts, right? So each explanation kind of is worth 2 points, because first of all, you have to recognize that it's the number of minority carriers that have enough energy to go over the barrier that matters, and then the fact that there are more minority carriers that have enough energy. So as long as you said something like that. But yeah, if you just said, okay, the ideal diode equation shows, okay, so dp over dp over ln over nd, and you just said, oh, nd goes down, so therefore I goes up, then it probably won't. I'd probably give you just 1 point, because you're not supposed to just simply use equations, right, to explain. It's not just math. You want to show that you understand physically what's going on in the device. The excess minority carrier concentration will increase, and because what? Why? And as long as you say why, it's because the potential barrier is lower. Okay, yeah, that's fine. Any other explanations that you want me to account for? Impedance to the flow of charge. Yeah, that's the same as the potential barrier being lower. That's right. Okay, reverse breakdown voltage. If a junction is more lightly doped, you actually end up dropping less voltage for the same applied bias. But also more importantly, the depletion width is larger, so you're dropping comparable voltage across a larger area, so the electric field is lower. So that means you need to apply even more voltage to get the electric field to be high enough to break it down. Okay, so those are the two parts to the explanation. Yes, Ross.
The depletion region, the depletion region gets smaller?
Yes, it does. Right, it gets larger, and you're dropping this. Let's say if you drop the same voltage across a longer distance, then the electric field is lower.
Okay.
So then you have to apply more voltage to get that electric field to reach the critical. Right. Yes? Yeah, if I had asked about increasing the doping, which I didn't, I asked what happens when you decrease the doping. If I asked, okay, if you increase the doping, yeah, then maybe you'd get, it'd be easier to break down. Yes, and partly because of increased chance of tunneling. Okay, for small signal capacitance, basically you had 2 parts. So under reverse bias, the dominant component of capacitance is depletion capacitance, not the diffusion capacitance. And the depletion capacitance depends on the width of the depletion region, which increases, so therefore the junction capacitance and therefore the small signal capacitance decreases. Okay? Now if you check the wrong box, but you have an explanation that explains that answer, then you definitely would get some partial credit, right? What I'm looking for is some reasonable, consistent explanation for your answer. Okay, and then finally, so why can't the voltage across the depletion region be changed instantaneously? So this is transient response. As long as you said that there's charge storage and it takes time to move charge in and out, then you'll get full credit. Why can't the potential barrier, unlike an MOS structure, why can't you just eliminate the built-in potential? That's because too much current flows and you get voltage drops in the quasi-neutral region. So as you try to apply more and more voltage across the depletion region, you actually end up increasing the voltage drops in the quasi-neutral regions rather than across the junction. And basically, you'll never be able to completely eliminate the built-in potential or counteract the built-in potential in a diode. Okay, so as long as you said something about series resistance at high current, so something about high current levels, series resistance becoming significant, then you should probably get full credit. Yes?
So I mentioned something about the circuit around.
I mean, for the last question, so there might be other.
So I mean, basically the series resistance, the whole circuit would.
Okay.
Because your current would increase on everything else as well.
Okay. Okay. What do you guys think? Is that valid? I mean, okay. So you're saying, what did you call it? Parasitic resistance? I mean, because it is a parasitic. I mean, it's not something that we purposely ever want to include in a circuit, but it exists, right? You can't get around it. Okay. No, that's fine. Yes, Ali. Yeah. So high-level injection does cause the current to decrease more gradually as you increase the applied bias. But it doesn't necessarily prevent you from applying a higher bias across the junction. Oh, I see. So you're saying, well, okay, because of high-level injection, the majority carrier concentrations are getting significant, and they might affect the junction voltage? Yeah. So if you have majority carrier diffusion becoming significant, that is the reason why the current doesn't increase with the same exponential slope as you increase the voltage anymore. But still, technically, you are still increasing the voltage applied, or decreasing the total potential drop across the depletion region. So technically, it's really series resistance at high current levels that limits your ability to affect the junction voltage any further. And yes, Andrew. Oh, okay, capacitance. Well, yeah, that's exactly how we model it. We model it as a capacitance, right? That you have to move charge. To change the voltage on the junction, you actually have to add and subtract charge. That's exactly the capacitance effect, the small signal capacitance effect. So technically, that's the same reason. Okay, great. How'd you guys do? Better than the second quiz? I think? Okay, we'll find out. But I hope so. I hope so. All right. So let's see. Today we'll have a relatively short lecture just to finish up the basics of the MOS capacitor. So last time I covered qualitatively what happens when you apply a bias to the MOS capacitor structure. So today we'll just derive some simple equations to allow you to see how the charge stored in an MOS capacitor changes depending on the regime of gate voltage bias. Okay, so for this lecture, and yeah, I guess in lecture we're only covering the case of an MOS capacitor with a p-type silicon substrate. Now during the discussion section this week, starting yesterday, Peng covered the case of a MOS capacitor with a p-type silicon, with an n-type silicon substrate. And I think the homework is for p-type or n-type silicon substrate. So if you want to get a head start understanding getting to do the homework problem, you might want to go to the discussion section. There's one more tomorrow. Okay, so there's three regimes that we care about primarily. So it's accumulation, and then depletion, and then inversion. Okay, so we'll just go through those three regimes of gate voltage today. Okay, so the first is accumulation. When you apply a voltage on the gate that attracts majority carriers to the surface of the semiconductor. So if you have p-type silicon, the majority carriers are holes. And to attract holes to the surface, you need to apply some negative charge beyond the flat band voltage. Okay, so more negative gate voltage than the flat band voltage is what you need to attract holes to the surface so that the surface becomes accumulated. So the energy band diagram we sketched qualitatively last time. And this time we're going to add some numbers here and give you some formulas for calculating some of these quantities. Okay. So let's review. This is assumed to be a N+ polysilicon gate, as the title infers. So the energy band diagram in the metallic gate is just that of silicon, and the Fermi level is at the conduction band edge. And then we have the silicon dioxide between the gate and the semiconductor. And so if we have a negative voltage on the gate, that sort of raises the electron potential on the left side. So basically, the way I like to think about it is just keep the energy bands in the silicon at the same location vertically. And then if you want to apply negative voltage to the gate, you raise the energy band for the gate on the left. Okay? That's the same as applying a negative gate voltage. Now, remember last time we mentioned that the difference in the conduction band edge between silicon and silicon dioxide is fixed, because the electron affinities of those materials are fundamental properties of those materials. So it's always 3.1 eV electron barrier and 4.8 eV hole barrier looking into the silicon dioxide. Okay? So we have an oxide with a large band gap of about 9 electron volts. Then we have some voltage. So there's going to be some voltage dropped across the oxide and some voltage dropped in the silicon. Now, an interesting key point, this is an approximation, but the Fermi level in the silicon is close to the valence band edge, right, because it's p-type. So if you have energy band bending in the direction corresponding to this gate bias polarity, basically we know that the surface is going to be accumulated, so the energy band is going to bend up. So the Fermi level is closer, it becomes closer to the valence band edge at the surface, right? That's right, hole concentration is higher at the surface. Right? That's why we call it accumulation. We have holes accumulating at the surface. So the total amount of energy band bending in the silicon really can't be too much. Right? It's not very large. So typically, the dopant concentration in silicon nowadays is like 10 to the 17, 10 to the 18. So the Fermi level in the silicon, deep in the silicon, is already close to the valence band edge. So there's really not much room for the band bending, for the energy bands to bend in the silicon. So we say that the total amount of energy band bending in the silicon, we'll just approximate that to be negligible, let's say 0. Okay? So remember the general equation that the gate, when we apply a voltage to the gate, okay, relative to the body here, or the bulk of the silicon, that voltage is going to be dropped partly, okay, well, there's a built-in voltage, a flat band voltage due to the work function difference between the gate and the silicon. So it'll be equal to the flat band voltage plus the voltage dropped across the silicon plus the voltage dropped across the oxide. So what I'm saying here is that in accumulation, the voltage dropped across the silicon is, we can approximate it to be negligible compared to the other voltages. So that's why we can write a simple equation down here that the gate voltage is approximately equal to the flat band voltage plus the voltage dropped across the oxide. Okay? So another thing to remind you of from last time, the Fermi level is a flat and constant across throughout the depth of the silicon, and that's because there's no current flowing, there's no DC current flowing in that direction, because of the oxide. The oxide blocks current flow. Okay. Okay. So looking at this energy band diagram, as I mentioned before, the difference between the Fermi levels gives you the magnitude of the applied gate voltage between the gate and the silicon. Okay, so that's an important thing to notice. Right, so you look at the Fermi level in the gate and the Fermi level in the semiconductor. That difference is equal to, well, in magnitude, Q times VG. So the greater you make the gate negative, then the more the bands on the left move up, and the more the Fermi level splits, okay, between the gate and the semiconductor. Okay, any questions about anything on this slide? Okay, so as a capacitor, we're interested. What's a basic equation for a capacitor that describes how a capacitor works? Q equals CV. That's right. Okay, so let's find out, so let's derive this equation for Q equals CV on this slide. So from the previous slide, I explained that the voltage drop in the silicon is negligible, at least approximately. All right, so from Gauss's law, basically all we need to know, so if we want to know the strength of the electric field, so this is the electric field strength in the oxide, okay, big E sub ox. Let me just go back. Okay, so remember the energy band diagram in the oxide is just a straight line, okay, because the electric field in the oxide is assumed to be constant throughout the oxide, okay. And the electric field strength in the oxide will depend on how much charge there is, like on either side of the oxide. The magnitude of the charge, actually it's the charge density on either side of the oxide. So the more charge you have stored on either plate, the higher electric field is within the oxide. Okay? So from Gauss's law, we can integrate the charge up to, well, going, let's say, starting from the top of the gate down through the gate and going into the oxide. The electric field strength is just going to be dependent on the total charge, either in the gate or in the accumulation region. So it's just convenient. Okay, we'll just call it the charge in the silicon, okay, minus Q time the accumulation layer charge divided by the permittivity of the material, which is silicon dioxide. Okay. So the key thing is just the total amount of charge in the silicon, which in magnitude is equal to the total charge in the gate. Okay. That divided by the permittivity of the silicon dioxide, that's going to give you the electric field strength. So to get the voltage drop across the oxide, we just multiply the electric field times the distance, the thickness of the oxide. Okay? And so we just plug in the formula for electric field, we get this equation for the applied, for the voltage dropped across the oxide. Now, this is an important thing to remember in this class. We actually, when we say C sub ox, that's the oxide capacitance, it is the capacitance per unit area. Okay, so that's something that might be a little tricky, because capacitance per unit area. So it's just the permittivity of the dielectric divided by the thickness of the dielectric. And permittivity of silicon dioxide, I mentioned last time, it's approximately 1/3 of the permittivity of silicon. And the permittivity of silicon, as you know, is 10 to the minus 12 farads per centimeter. So it's approximately 3.33 times 10 to the minus 13 farads per centimeter. But to be precise, sometimes on the homeworks or the exams, I'll ask you to use a more precise number. It's actually 3.45 times 10 to the minus 13, more precisely. Okay. But anyway, we'll always give you the number to use for the calculations. Okay. So, yes, question, Josh? Oh, so the question is, does it make any difference? No, it's just the numbers that you come out with. I mean, so for convenience, we like to say it's just 3 times the permittivity of silicon, but you know, if you want to be precise, then the value is 3.45. Yeah. But as long as you remember it's roughly 1/3 of the permittivity of silicon, you're fine. Okay. All right, so we come up with a simple equation that so this is charge coulombs per centimeter squared. Yeah. So the charge, so this is the areal, did we not say this? Okay. So it's the accumulation layer charge density. So this is, when we say charge density, oops, we're looking at charge per unit area. Okay, because, so looking down at the surface of the silicon, like how much charge you see per unit area, that's what we're talking about here. Okay, so the accumulation charge per square centimeter is just going to be is proportional to the oxide capacitance times a voltage. It's the voltage difference So it's the voltage difference between the gate voltage and the flat band voltage. Okay, so remember for a normal capacitor is Q equals CV, but we're talking about small signal capacitance here. So the total amount of accumulation charge in the silicon is going to be equal to the capacitance of the dielectric times some voltage, but it's the voltage sort of beyond the flat band voltage, right? Because at flat band, you have no band bending, you have no charge in the semiconductor stored. Okay, was there a question? No, okay. All right, and the sign here reflects the fact that you have the gate voltage. Okay, so VG minus V flat band is negative, and we know the charge in the silicon is positive. That's why you have a minus sign there. So this is actually a positive accumulation charge per unit area in the silicon. Okay. All right. So let's start to plot. I'm just going to start a plot here of the gate voltage, the charge in the silicon, charge per unit area in the silicon as a function of gate voltage. So let's see, flat band voltage. Is the flat band voltage here positive or negative? Does anybody remember? If it's positive and negative, it's I think it's negative. Okay, so the plot will look something like here for the people who are watching this. So it's going to look something like this. Slope is going to be equal to the areal capacitance. Okay, so if you apply a negative voltage that's more negative than the flat band voltage, then you're just going to increase the charge density in the gate and in the silicon. Okay, now let's see what happens under depletion. Oh, and most of the voltage that as you increase the gate voltage, you're just increasing the voltage dropped across the oxide. Okay, now the situation is a little bit different in depletion. So that's for the gate voltage greater than the flat band voltage, but smaller than the threshold voltage. So let's see what this charge density looks like. Okay, so first let's look at the energy band diagram. If you put a voltage that's more positive than the flat band voltage, that means you're moving the bands on the left down, right? More positive, so it's more lower electric potential for the electrons. So you're moving the energy band diagram down on the left, and you're causing, so therefore the electric field is going to now point in the opposite direction as in the case of accumulation. But now the energy band bending is in the opposite direction. Okay, so you're sloping upwards to the right rather than downwards to the right. Okay, so you're again going to have some voltage dropped across the oxide, and again, the potential barriers here are 3.1 eV and 4.8 eV and so on. So the energy band bending will be sloped the other way. But now you actually have lots of room to bend the energy bands in the silicon, right? It's not like the previous case where there's really not much room for the band edges to move away from the Fermi level. Okay, so what happens physically is if you put a more positive voltage on the gate than the flat band voltage, then that positive charge on the gate is going to repel the positive mobile charge in the silicon. It's p-type silicon. So it's going to repel the majority carriers away from the surface. And when the mobile charges move away, they leave behind ionized acceptors that are not compensated in charge by the mobile positive charge. So you end up with net negative charge at the surface, which makes sense because if you're increasing the voltage on the gate positively, that means you're putting positive charge on the gate. And that means you must be inducing negative charge in the silicon. So the bottom line is the negative charge, where does it come from? It comes from the depletion region. So there's this region at the surface that is depleted, and the negative charge in the silicon comes from the ionized acceptors, okay, in the silicon. Okay, so basically this negative charge negative charge in the silicon is due to acceptor ions. Okay, so as you so we can actually use well, let's see, yeah, the depletion approximation again. So let me, I have some notes. So if you plot the charge density versus distance, let's call it x, it's going to look like this. So minus QNA, and then there'll be some depletion depth. So there's some depth. So this is a depletion approximation here. So there's some depth to which the silicon is being depleted underneath the gate oxide. Okay. So we're just assuming that the holes are the whole concentration is negligible in the depletion region, and after the depletion region, whole concentration is comparable to the dopant concentration. So there's no net charge in the silicon beyond the depletion depth. Okay. So if we deplete the surface of holes, then that means the surface region is becoming less p-type. And so the Fermi level, again, is constant. And then at the surface, you see that the valence band is getting farther away from the Fermi level. So this means that the semiconductor is less p-type at the surface. Okay, so that's why we call it depletion mode, or depletion region. Okay, so we can use the depletion approximation just like we did for the metal semiconductor contact and for the p-n junction. So we just assume the charge density is constant, equal to the dopant concentration or proportional to the dopant concentration in the depletion region, down to a certain depth. Okay, and then we can use Poisson's equation to determine so that determines the slope of the electric field distribution. And we can integrate twice to obtain the total, the electric potential, like the voltage drop. And the total voltage drop in the silicon is just defined to be phi sub s. Right, so we just integrate twice and apply the boundary conditions. And you can get this equation for the depletion width, which I sort of introduced last time. Basically, it's the exact same equation as we derived for the junctions in the past, except that the total voltage drop in the semiconductor now is not the built-in potential or VBI minus VA. It is phi sub s, right? That's just a definition, the total voltage drop in the silicon. Okay. Qualitatively, does this make sense? All right. Okay, so now let's come up with a more precise equation then for all the voltage drops in this MOS system. So remember, I'm just going to repeat again, when you apply a gate voltage, that has to be equal to the flat band voltage plus the voltage drop across the silicon plus the voltage drop across the oxide. Okay. Oh, that's what's repeated down here. Okay, but now the question is, well, what is the voltage dropped across the oxide? Well, it's just going to be equal to the total charge in the silicon, just like before, divided by epsilon, the permittivity of the oxide. Okay, but now, so the terminology we're changing here, it's always the total charge density in the silicon. So in depletion, if the surface is in depletion, we call it the depletion charge. Okay? And if the silicon is accumulated, we call it the accumulation charge. It's just this terminology. Okay? But in each case, we're just talking about the total charge density in the silicon. Okay, so the equation is essentially the same. And therefore, the voltage equation is the same. The voltage dropped across the silicon is just going to be equal to the electric field strength times the thickness of the oxide. Okay? So now, Q depletion, what is that total charge in the silicon? Well, it's just the area under this curve, right? This is Q depletion. Right? So you just integrate all this. So this is charge per cubic volume, and then you multiply by the depth, this width, and you get charge per unit area. Okay, so that's what Q depletion is. It's just the charge per unit area in the depletion region. And if you plug in the equation for W, you get this square root expression here. Okay? So this term here is just Q depletion over C ox. And that's equal to V ox. That qualitatively makes sense? Okay. All right, so let's see. So how does that surface potential vary as you change the gate voltage? Okay, if you do it mathematically, you have this expression, for VG is equal to the sum of all the voltage drops in the system. And then you can use the binomial, what is that, that formula. This is like a quadratic equation. You can solve for the square root of phi sub s and find that phi sub s is this kind of complicated looking function of the gate voltage. So bottom line is the only reason to look at this equation really is to see, as you increase the gate voltage above the flat band voltage, how effectively are you changing or affecting the potential drop, the voltage drop in the silicon. So basically, I had a little demo here. Okay, so in depletion, okay, so let's say this is my one hand is the gate, okay, and this little, do you understand, see that bear pin? Okay, little cow bear pin is the surface channel potential, okay, and let's say I'm fixing the potential of the silicon at the bottom. And see, if I want to change the potential at the surface of the silicon, which is the little denoted by the cow bear, basically I don't have a direct connection to it. I'm capacitively coupling to it through the gate oxide. So basically, by increasing the gate voltage, I'm pulling it up, and I am pulling up the bear, but I'm wasting part of my effort by increasing like the voltage drop across the silicon, right? So basically, there's some capacitive coupling ratio there. So that's basically what this equation represents. It's like as you increase VG, ideally what you want to do is change the voltage at the surface of the silicon, but you can't do that because it's a capacitive voltage divider. Part of that voltage is dropped across the oxide, and part of it is wasted across the silicon. Okay, so eventually you should be able to change the voltage dropped across the silicon enough to change the surface from p-type to n-type. So that's what I introduced qualitatively last time. If we actually can, let's go down, skip down. If we're bending the bands in the silicon, okay, so by applying enough gate voltage, we can induce this voltage drop in the silicon. And if that voltage drop is enough to make the surface, okay, so the Fermi level is very close now to the conduction band edge, so the surface becomes n-type. But the bulk, right, the Fermi level is close to the valence band edge, the bulk is p-type. Right? Okay, so if this distance here, let's use a different color. If this distance between the Fermi level and the valence band edge is the same as this distance at the surface between the Fermi level and the conduction band edge, we say, well, that the surface has become strongly inverted, okay, so that it is just as much n-type at the surface as it is p-type in the bulk. And this is what we define, as I mentioned, it's a little bit arbitrary. We define it as the threshold condition, so the threshold of strong inversion, technically. Okay, so last time we introduced this in the bulk. This is EI, EC, and EV. And if the bulk is p-type, okay, and this is defined to be phi sub f, q times phi sub f. So if this, okay, so let's just draw this here. So I'm just sketching the mid-gap energy, which approximates E sub I, the intrinsic Fermi level. So what this is saying is that, okay, this distance here is equal to this distance here. I'm not sure if you see it. So basically, the difference between the Fermi level and the intrinsic level is the same in magnitude at the surface as in the bulk, okay, which is saying the same thing. It's just as much n-type at the surface as it is p-type in the bulk. So you can see, hopefully from this sketch, that this distance plus this distance, that's equal to the total band bending in the silicon. And so that's why we just have 2 phi f at the threshold condition. Okay? Now, after that, as you increase the gate voltage further, bring it the left side down here, there's really not much further distance for the energy bands to bend because these conduction band edge is now very close to the Fermi level. And so we just say that we can approximate that okay, so W sub t is defined to be the depletion width at threshold. Okay, so it's the same formula as before, but now notice that the total potential drop in the silicon is just, rather than phi sub s, is 2 phi f. Okay, so at the threshold condition, that's basically the definition of phi s, 2 phi f. So we assume then that, okay, so this is the definition of the threshold condition. So then that's an important voltage, actually, for us to keep in mind, because that means that if we apply a gate voltage that is that large, the surface becomes n-type, we actually can start to accumulate electrons at the surface rather than continuing to deplete the bulk of the silicon. Okay, so what that means is that as you increase the gate voltage to be more positive, you're adding more charge, positive charge on the gate. That means you have to add more negative charge in the silicon. So once you reach the threshold voltage, most of the negative charge in the silicon that you're adding is due to electrons that are mobile rather than further depleting the surface more deeply. Yes? How do you calculate the thickness? Okay, so what we approximate is that once you apply a gate voltage higher than the threshold voltage, then you'll start to accumulate electrons at the surface. Now, in reality, you actually already start accumulating electrons at the surface once this intrinsic, energy level, E sub I starts to fall below the Fermi level. Then, in principle, you're already starting to form an inversion layer of electrons. But the concentration of electrons is still negligible compared to the concentration of ionized dopants. So that's why we sort of say, okay, we consider that to be negligible. We only consider the mobile electron concentration at the surface to be significant once it reaches the ionized dopant concentration level and beyond. Okay. And was your question about the thickness of the inversion layer? Okay. Yeah. So the thickness, we'll cover that probably next week. The thickness of this layer of electrons, this inversion layer of electrons at the surface, is on the order of 1 to 2 nanometers. So it's very small compared to a typical depletion width. And it depends on the gate voltage, right? The higher, the more positive the gate voltage, the more strongly you're attracting electrons to the surface. So on average, the inversion layer becomes thinner as you increase the gate voltage above the threshold. Okay, so, but just bottom line is that, the threshold voltage is important because that's the voltage at which we just approximate the surface to have a lot of electrons. So if you're looking at an MOS capacitor in a transistor, that's the voltage at which a lot of current can flow between the source and drain regions. Because now you have N plus source, N plus drain, and you have an N-type surface region that forms a channel between those source and drain regions. So you can actually start to conduct a lot of transistor current. So threshold voltage is an important parameter for MOS devices. So it's important to actually remember the formula for the threshold voltage. So again, it is defined to be the gate voltage. Let me be a little precise here. It is, in this slide, it is the gate voltage relative to something, right? Voltage is always a relative term. So it's the gate voltage relative to which voltage? It's the silicon substrate in this case, right? So it's the gate voltage that you need to apply relative to the voltage on the substrate that will cause the surface to become inverted, strongly inverted to be the opposite type as the bulk. So it's equal to the flat band voltage plus 2 phi f. Okay, so the key thing to remember is the gate voltage is always equal to the flat band voltage plus the voltage dropped across the silicon plus the voltage dropped across the oxide. So to remember the formula for the threshold voltage, you just have to remember that. Okay, and at threshold, remember that the voltage dropped across the silicon is just 2 phi f. The voltage dropped across the oxide is equal to the depletion charge at threshold. Oops, that's this. The depletion charge at threshold over the oxide capacitance. So it's like V equals, well, Q equals CV, right? So V, the voltage drop across the oxide is just equal to Q over V, over C, right? So it's the Q depletion charge, so the total charge per unit area in the silicon divided by the oxide capacitance per unit area. Did I say the wrong thing? So it's charge per unit area divided by capacitance per unit area. That gives you the voltage drop across the oxide. Yes? Okay, so can we go over if phi s equals 0? Oh, yeah, okay. Phi s is 0. That's the flat band condition. So that's this. So this is flat band. Okay, so if you apply a voltage, so here's the Fermi level in the metal. Okay, this is, let's say, N plus silicon gate and P-type silicon. So P-type silicon, Fermi level is like around here. No, so this is, you get flat band condition when you apply a voltage. Remember, the difference between the Fermi levels, so there's a Fermi level here in the metal, in the gate, Fermi level in the silicon. They're vertically offset, right? So that vertical difference, that's equal to the applied bias voltage, right? So that, so you know, because the Fermi levels are different in the gate versus the silicon, you know that there must be a voltage being applied to the system. And whatever voltage is being applied here is just enough to completely make the energy band diagram flat. Specifically in the silicon, it's flat. So this is the flat band definition of the flat band condition. It's basically you're applying a gate voltage, which is defined to be the flat band voltage that causes no band bending in the silicon. And so this is where phi sub s really is precisely 0. Now in accumulation, we're saying, oh yeah, there's a little bit of band bending, but it's also negligible. Okay? So only under depletion can you get really significant energy band diagram, energy band bending in the silicon. See, so here we have significant band bending, close to 1 volt of energy band bending in the silicon. And that's because the silicon surface is being depleted, becoming less p-type, and eventually at the surface becoming n-type. Okay. Yeah, so okay, so this little demonstration thing. The reason why you have to do voltage sharing. Okay, so if as you change the voltage on the gate, you're adding or subtracting charge to the gate, and therefore you have to add or subtract charge of the opposite sign in the silicon. Okay, and if that charge is not easily supplied, so under accumulation, you have a lot of mobile holes that can be supplied from the contact. Let's go back here. So under accumulation, you can easily supply holes as needed into and out of the backside contact. So when you're changing the gate voltage, basically you have holes easily generated to provide this necessary charge on the opposite electrode. Right? You're applying negative charge to the gate. You need some positive charge to come from somewhere, and it's easily coming from the contact. So basically, it's equivalent to moving this thing up and down. Like basically, you can have charge coming easily in and out to move with to adjust to the gate voltage. So you don't have to worry about this sharing the voltage drop in the silicon with that in the oxide. Okay, same thing. So, but in depletion, you're adding positive charge to the gate, right? You're biasing the gate more positively. Ideally, you'd like to have negative charge coming from somewhere in the silicon, but this is p-type silicon, so the electrons don't come about very easily. So the easiest way to get negative charge in the silicon is just to deplete the surface to get ionized acceptors exposed. And so because the concentration of charge is fixed by the dopant concentration, you have to deplete to a certain depth to get the necessary amount of charge in the silicon to match the charge on the gate. And that's why you end up sharing the voltage drop across the oxide with a significant voltage drop across the silicon. Okay, so the voltage drop occurs across the silicon only really in depletion, not in accumulation. And we're going to cover inversion momentarily here. But okay, I just want to make sure, does anybody have any questions about the threshold condition and the equation for the threshold voltage? So this is defined to be the gate voltage where the threshold condition is reached. Okay, so qualitatively, you actually will have a homework problem on this, but in general, okay, so these are plots of, okay, so blue curves show the threshold voltage as a function of the dopant concentration on a log scale. Let's just look at the blue curves for now. For the homework, actually, I think you're going to do the black curves, but anyway. So as you increase the dopant concentration, the threshold voltage increases. Okay, so qualitatively, if you make the substrate more p-type, it becomes harder to invert the surface. Does that make sense? Qualitatively, because you have to, you have to apply more voltage to change the surface from p-type to the equally n-type at the surface. So hopefully, qualitatively, that makes sense. The more heavily doped your silicon is, the higher the threshold voltage will be. Okay, what about the oxide thickness? As you increase the oxide thickness, your threshold voltage is going to go up. Okay, so qualitatively, that should hopefully also make sense. Let's think about it. That's equivalent to making like this oxide. I mean, that's okay. If the oxide is thicker, basically you're going to end up dropping a larger voltage across it, right? Because the voltage drop across the oxide is the electric field, which is determined by the charge, times the thickness. So if you make the oxide thicker, you're going to waste more of the voltage that you're trying to induce in the channel. You're going to waste the voltage you apply, more of it's going to be dropped across the oxide. So then that means you have to apply a larger voltage to get the surface to be inverted. Okay, so that's qualitatively. Okay, so what happens when you go beyond inversion? Okay, so now once the surface becomes heavily n-type, let's say sometimes you might have in a transistor you'll have some heavily doped n-type regions nearby. They can easily supply electrons in and out of that inversion region. So generally what we say then is that we actually, beyond, if you apply a gate voltage greater than the threshold voltage, there's really not much more room for more band bending to occur. So we'll just say, okay, approximately the total energy, the total voltage drop in the silicon will just stay at 2 phi f. It won't go much higher. Okay, that's just, it's an approximation. So we just say there's a maximum depletion depth of W given by this equation, and just has 2 phi f for the voltage drop in the silicon. Yes, question? Why does that maximum exist? It's actually not precise, but it's for the same reason. If we increase the gate voltage to be more positive, yeah, there'll be a little bit more voltage drop in the silicon, but the conduction band is already pretty close to the Fermi level, so you can exponentially, okay, as you apply more voltage and have more energy band bending in the silicon, you're bringing the conduction band closer to the Fermi level, and you're exponentially increasing the electron concentration, right? As you bring the conduction band closer to the Fermi level, you're exponentially increasing the electron concentration. So you actually don't need to, if you're linearly increasing the gate voltage, so Q has to increase linearly with the gate voltage, you don't really have to move the bands too much to get that linear increase in electron concentration at the surface. Right? So the energy bands don't really move too much once you form a strong n-type layer at the surface. It has nothing, no, it's more basic than shielding. It's nothing to do with shielding. Yeah. Okay. And we can go through this, but it's pretty simple math. Remember, Q equals CV. Remember, so in accumulation, is the V is the voltage below or beyond the flat band voltage. In inversion, the V in this Q equals CV equation is the voltage above the threshold. Okay, so just remember Q, this is a MOS capacitor. So the inversion charge, the mobile charge in the silicon is going to be proportional to the capacitance times the voltage beyond the threshold voltage. Okay, so as you increase the gate voltage beyond threshold, you're just going to increase the concentration of inversion layer electron charge in the silicon, rather than depleting further the silicon to have more depletion charge. Okay, all right, that's it. So today we have Chinese food out in the social hour. I hope to see some of you there.